marathon of reactions. Let's go through a couple more. And rather than nitration, let's think about sulfonation. And same idea, 3 steps. We're going to generate strong electrophile, react with the aromatic system, and regenerate the aromatic system. So with benzene, what you would find is that if you use this compound SO3 plus sulfuric acid, I'll condense that one. This will now sulfonylate, generate SO3H here. And this reaction is particularly useful because it's reversible overall. And we might not get into too much as to why that's important, but it is. And so we need to have the same idea of generating a strong electrophile. Now, this is a case where there's a lot of chemistry actually that's going on behind the scenes, and it turns out that this SO3 itself, sulfur trioxide, is a strong electrophile on its own, but a lot of times it's also written to form a strong electrophile with sulfuric acid. I don't want us to get too caught up in those details. I notice the Sorel textbook has several equilibrium steps that are drawn before this, or acid-base chemistry steps, I should mention, before this. We'll just mention one of them. One thing that's kind of neat, though, is that this compound itself is a gas, so it's a little more difficult to work with. But when you mix these two together, then you have a liquid you can work with, but it's known as fuming sulfuric acid. I've never worked with this. I don't want to. As you can imagine, it's going to be a sulfuric acid, but it's actually quite reactive because it has this sulfur trioxide gas in it. But going back to our steps, this compound here could, as you mentioned, actually react. However, in the presence of sulfuric acid, again being a very strong acid, it likely just protonates this. It's one of the species that's formed. So we have something that looks like this. So we have this sulfur now with a positive formal charge. Let's make that oxygen a little bigger here. So we have a very strong electrophile again, plus we'd have the conjugate base of sulfuric acid. So now we can have same reaction that we've seen before. Let's have our strong electrophile attacked by benzene, paying that cost of breaking aromaticity from carbocation, plus we're going to have, I'll just keep this one as the OH, it's fine. And now we just need to restore our aromaticity. So this is also going to have, say, water around. So the sulfuric acid would have water. So we'll use that. So our base. It's supposed to be a 6-membered ring, all equal sides. It says that SO3H. And we reformed our aromatic system. So same idea, generating a strong electrophile here in the top middle, or the middle of the page, I should say, paying the energetic cost to destroy the aromaticity in the system, forming the new bond with the strong electrophile, deprotonating to generate our final product. And going here to the top part with the equilibrium arrows, this is very useful because you can use Le Chatelier's principle to push this reaction back and forth. So if you have this sulfuric acid and this fuming sulfuric acid concentrated, the reaction is going to go forward to the right. If you make it very dilute, add a whole bunch of water in the reaction, then the reaction is going to go to the left. And we may not have much time to go over this, but this is useful as either what's known as a blocking group over here in the upper right, or a directing group, because you can take this group on and off. So we earlier saw protecting groups, as groups you can introduce and remove for certain reactions. Here you can add this SO3H, and there's certain synthetic reasons why you would want to do that. All right. So again, fast, but hopefully seeing the common themes here. How about two more reactions to get to our 5? And this one will cover a couple more features with. And the last two are named after these two individuals, Friedel and Crafts. And the first one is going to be an alkylation. That's supposed to say alkylation. Sorry, I'll leave that on the top. It's not written down yet. So what sort of reaction might this look like? Let's put it over here to save us a little bit of space. So let's take benzene, and you react this with, say, this 2-chloropropane. And in the presence of AlCl3, we've alkylated the benzene right now, or we've added an alkyl group. Let's just put it in the same spot. So somehow we've formed a new carbon-carbon bond, plus we release HCl, plus we get AlCl3 back. So let's see if we can now come up with a mechanism to explain this reaction and apply the same things that we've seen before. We'll write it out here again for emphasis. So let's generate a strong electrophile. So we did this on Thursday with bromine up here. So just Br2 and FeBr3. Now what we can do is, let's say that the chloro substituent should react in a similar way to bromine. And rather than that, using an iron tribromide, FeBr3, we're going to use aluminum trichloride. But it's going to serve the same purpose. And let's see if that gives us our product. So let's take our isopropyl group here. So 2-chloropropane, let's just tilt it on the side here. So we have all these lone pairs of electrons, just like we saw with bromine. And aluminum trichloride. This is going to act as our Lewis acid again, just like the iron tribromide did. So overall, what we want to do is generate the strong electrophile. So let's have the chloro group donate a pair of electrons to the aluminum. So we'll form a new bond between the chlorine and the aluminum. And just like what we saw with the bromine, now the chlorine is going to bear a positive formal charge and the aluminum a negative formal charge. Now, it's not entirely clear if this always happens exactly like this. It's probably somewhere in between, but we're going to write this in the next step as generating a formal carbocation. So let's break the carbon-chlorine bond. And now we'd be left with a carbocation plus AlCl4. Negative formal charge. So this would be our strong, I'm sorry, it's green, our strong electrophile. We have a carbocation, which is our strong electrophile. So that actually looks pretty good, because now all we have to do is probably let's put that into our regular, we'll call it the regular reaction mechanism. Let's take benzene and let's rewrite it down here. We're going to turn our carbocation around here. And let's have our benzene form a bond. Sorry, it hit the right carbon. Looks like it almost missed it. Right there. Forming a new carbon-carbon bond. So there's our group that we've added. Now have a carbocation on our iridium ion. And all we have to do is deprotonate here. So we'll have our aluminum trichloride. It looks like we get, tetrachloride. It looks like we get this back in the end. So let's use the electrons in this aluminum chlorine bond to pick up that proton, reform our aromatic system. So we'd have now our alkylated benzene plus here hydrogen chloride plus over here we're left with AlCl3. Okay, so then we've alkylated. So Lorianne asked a great question about what about adding purine to prevent the HCl from forming. So yeah, if you have a compound that you don't want HCl forming, you'd like to also add a base, and that would be a very good thing to do. A challenge here is probably that the purity would also react probably with the Lewis acid, with the aluminum trichloride, and then form a complex and kind of destroy the Lewis acid species. So it's a serious challenge. You'd want to in the end have something that's going to say, soak up the HCl if we were concerned about that. So you might slowly add in some sort of base or have another base present as well. So we're just assuming in this particular case that the HCl doesn't have an effect. But yeah, you'd want to somehow try to neutralize this as it's going along at the end. The problem is that it's not like all of these reactions are happening at the same time. Like 1 mole of this is always being converted over. Some are faster, some are slower. So that's a real hassle that you have to work with. So it's a great point. And it's a real challenge in a lot of these reactions is to balance the reagents. So that you would have something that reacts with the HCl, but also doesn't react with the Lewis acid. So I'm not giving you a direct answer necessarily, because it would be a balance between is the compound sensitive enough or not sensitive enough, I should say, to HCl versus adding a base.